So let me write the formula for the nth derivative of f again. So nth derivative of f at point z is n factorial upon 2 pi I integral over c f of s upon s minus z to the power n plus 1 ds, where conditions on f and z are f is analytic on and inside a simple closed contour C. So this is C, and this function has to be analytic on C and inside C. So if you want to use this formula, these conditions have to be satisfied. And then this z at which the nth derivative function is well defined and analytic, and this formula is applicable if the point z is inside. So if the point z is inside this simple closed contour C, I am using the word contour instead of curve all the time, because while drawing I am drawing simple closed curve and this looks smooth also. But then in examples we saw that your contour can be like this, which is not a smooth curve, but it is piecewise smooth. That means the points at which the curve is not smooth are finitely many. So except for finitely many points, the curve is smooth, and then this is valid contour for the purpose of integration. So this is a better situation whereas this is perfectly alright, this is piecewise smooth. And the best perhaps situation is the symmetric curve like circle, where the function that describes the curve is easy. So for example, this is mod z minus z naught equal to r, where this is z naught and this is r. Alright. So this is what is all about this formula, okay? That is, the nth derivative is obtained in this manner. And the important corollary that we saw is that if f is analytic, so if f is analytic at some point z naught, then the nth derivative function is also analytic, We got this from this formula because this is obtained from just the assumption that f is analytic. So if f is analytic, you get formula for f first, where this is 0, and therefore this is 0, and this is fs upon s minus z. So if f is analytic, then we get formula for f for the points applied to the points which are interior to. And then by using that formula for n equal to 0, we get formula for first derivative. So underlying assumption remains f is analytic. So once f is analytic, you get first derivative, and from formula for the first derivative in terms of integral, you get the formula for the second derivative. Then you have formula for the second derivative in terms of integral, and then from that you get the formula for the third derivative. So that is how it is. So this is the more beautiful part of the theory, that the function values are given in terms of integrals, and the value of s is on the boundary. See this, s runs over the boundary, whereas z is inside this. So values of the function and all its derivatives inside the curve are obtained in terms of the values of the function on the boundary. So this is a very striking phenomena, in the sense that the boundary values can be used to compute values inside the curve, okay? And that makes the difference between real and complex analysis, because then This type of statement is not available in real analysis. Function may be differentiable at one point and function may be differentiable 2 times but may not be differentiable 3 times. Okay, whereas this corollary will enable us to find out Taylor series expansion of the function just on the basis of the assumption that it is analytic. So if it is analytic at z0, all the derivatives of all orders at point z0 are analytic. So such function will have Taylor series expansion, because if you remember from real analysis, we need all order derivatives for Taylor series expansion, which here you just get by assuming only analyticity. Okay, so this corollary is a very striking distinguishing phenomena in complex analysis, which there is no counterpart in real analysis. Okay, so this is typically a complex analysis corollary. All right. Now let us see some applications of Cauchy integral formula. So applications of Cauchy integral formula. First among the notable applications is Liouville's theorem. Liouville, Liouville's theorem. Now again, once you have one typical case of a complex function, now as an application you will get a series of statements like this. So this is the first among the statements that I am going to prove by using Cauchy integral formula. So what is Liouville's theorem? If f is an entire function and if f is bounded, then f is constant. Then f is a constant function. Complete this statement. Now, as I have been telling you all the through, that one has to compare a complex statement with the real one. Okay. So what is entire function? Yes, function is entire means it is analytic everywhere. So entire means analytic everywhere. Everywhere. And then if it is bounded, then f is a constant function. Now if you consider a real variable, okay, real variable, do you have a function which is infinitely differentiable and bounded? So can you give example of a infinitely differentiable real function which is bounded? That is question. Then in that case you can compare this statement with the real variable theory. Okay. So remember, always the idea is to have a stock of examples with you. All right. So can you give me example of a function which is infinitely differentiable and bounded? Very simple example. The simplest possible example I can think of is sin x. Sin x. Sin x, isn't it bounded? Yes, it is bounded. It is between -1 and 1. Is it infinitely differentiable? Yes. Derivative of sin x is cos x and derivative of cos x is minus sin x, and then therefore again derivative of that is minus cos x, and so on. Okay. Cycle of 4, the derivatives repeat in fact. So it is infinitely differentiable at all points on the real line. It is bounded, but is it a constant function? No, definitely not. Sin is not a constant function. Okay. In fact, it is a periodic function, continuous, and varies on to -1 to 1. So definitely this type of statement is again not available in real variable theory. So this is typically complex phenomena, and immediately as an application one can say that sin z and cos z are not bounded. Okay. Something that would surprise us. So by Liouville's theorem we will get that sin z cos z are not bounded. Okay. So let us see the proof of the Liouville's theorem as an application of the Cauchy integral formula. Okay. So let me write the formula for the nth derivative again and obtain a bound on the absolute value of the nth derivative at point z. Okay. So first point to be noted is, so let me again write this. So under the assumptions of this theorem, so this is an entire function. So you may take any point and any neighborhood of that function. Okay. So let us first of all consider, let z naught be any point, be any complex number, any complex number. If we show that fz equal to fz naught for all z, then f is constant. So I have chosen a point arbitrarily. Okay. Now you can consider a circle with center at z naught and radius r. So think of this circle now. Okay. Circle with center at z naught and radius r. Okay. So let me call this curve positively oriented as CR. Okay. So CR is the circle with center at z naught, radius r. Now we want to apply Cauchy integral formula for f around this curve CR. So the curve under consideration will be CR, and it is a good symmetric curve because it is a circle. So what can you write from Cauchy integral formula? It is written there already. It is already written there if you see here. So now by applying the formula, now the curve that I have drawn has gone to the other end of the board, and now I am writing here. So can you see this? Okay. So nth derivative at z naught, okay, is fz upon z minus z naught to the power n plus 1 dz where this curve under consideration is CR. Okay. Now what is f? F is analytic. Where it is analytic? It is analytic everywhere because it is given to be entire function. So since it is analytic everywhere, it is continuous everywhere. So f being analytic everywhere, it is continuous. And therefore on any curve C, curve being a compact set, a continuous function will have upper bound if the values are varying over a compact set. So there will be some constant m on this, okay, CR. But as such you don't need that constant because f is bounded throughout the complex plane, not only on CR. Okay. So f already has an upper bound. So we have used both the facts that it is entire and bounded. So further f is bounded. Bounded. What do you mean by bounded? What do you mean by constant function being bounded? Because complex numbers cannot be compared. So what is upper bound means what? Absolute value is bounded. So therefore there exists m positive such that mod fz is less than or equal to m. That is definition of bounded. For all z in C, is bounded everywhere. Now with this information that absolute value of this is less than or equal to m. This is circle with center at z0 which I have drawn there with radius r. Can you find a bound on nth derivative at z0? Okay. How do you find the bound on nth derivative of z0? Formula is right in front of you. So how will you proceed? How do you proceed means what? Take the bound, take the absolute value on both sides, okay, and then you know that this absolute value is less than or equal to m into L. We have proved m into L theorem, which we have called m into L theorem, where what is m? M is bound of the function, and what is L? L is length of the curve. So that theorem we have to use. Remember, situation of theorem should be clear. So when you have this bound on both sides, it is clear which theorem is to be used. Okay. It should not happen that it is not clear as to which theorem is to be used. Then it is failure of that particular theorem in fact. So, and that is never the case. So if you take the upper bound, you take the absolute bound and you want bound. It is clear that you have bound on this z minus z0 anyways is r. Mod z minus z0 is r because this is circle with center at z0 radius r. So for all z here, mod z minus z0 is r. So there is already not just bound, exact value of this. Okay. So mod fz upon z minus z0 to the power n plus 1 is less than or equal to, this is less than or equal to n, and this mod is exactly equal to r. Mod z minus z0 is r. So this is r raised to n plus 1. This is true for all z. And then this mod is n factorial upon modulus of I is 1. So mod of nth derivative, you get now bound on that. So mod of nth derivative at z0 is less than or equal to n factorial upon 2 pi times, what do you get? M upon r raised to n plus 1. M upon r raised to n plus 1 into length of CR. Length of CR is, this is circle, so 2 pi r. 2 pi r. So this 2 pi will get cancelled. This r upon r raised to n plus 1 is r raised to n. So you get mod of nth derivative at z0 will be less than or equal to n factorial m upon r raised to n. N factorial m r upon n factorial m upon r to the power n. Okay. Now, in particular, if you take n equal to 1, then what will happen? In particular, if n is equal to 1, so in this upper bound on nth derivative, what do you get? So in particular, mod of nth derivative at z0 is less than or equal to first derivative. Let me write just first derivative at z0. So n is 1, see m upon r. Now what was Z naught? What was Z naught? Z naught was any point. Z naught was any point in the complex plane. So whatever has happened here for Z naught is true for any complex number. Is this clear? Whatever is true for Z naught here is true for any complex number. Therefore, but let me write, but Z naught is any complex number. Any complex number. So, for any Z, what will happen? F dash Z is equal to, is less than or equal to, mod F dash Z is less than or equal to M upon R. Where what was R? R is radius of the circle with center at Z. So, essentially what we have done, take any point and take any radius. Then you have this bound where this is radius. If you want this radius, that is also true. Because what all we need is F is analytic on and inside. But F is entire. Everywhere it is analytic. That means you can take R as large as possible. That means you can take R to be as large as possible, because if I take this Z, I will take a large R. And what must happen? F is analytic on and inside that circle. But yes, it will hold because F is entire function. So therefore we can take R tending to infinity, because if I have some positive bound here now, okay, I can take R so large that that will be still less than that. Okay, so that means we can take limit of this as R goes to infinity. Whereas this will not change. This is point Z and you are considering circles around that point and checking whether you can apply this Cauchy integral formula. But you can take large R and still you can apply. How large? Infinitely large, because it is entire function. Is this clear? Is this idea clear to you? Therefore we can take limit as R goes to infinity in this, and then we get that this will become 0, that is mod F dash Z is 0, that is F dash Z is 0. So then we get, so taking limit as R tends to infinity, taking limit as R tends to infinity. So writing R going to infinity, we have mod F dash Z equal to 0. That is F dash Z is 0 for all Z. But then we have seen that F is analytic and its derivative is 0, then the function must be constant. Okay, so Fz is constant. So Fz is constant. So if F is entire function which is bounded, then it has to be constant. Entire bounded function has to be constant. All right. This is application of the Liouville application of the Cauchy integral formula, and then in turn the formulae for the nth derivative. Okay. All right. So as an immediate corollary to this, let me write an immediate corollary of this. Let me write that sin Z and cos Z are not bounded. Okay. The function sin Z, the functions sin Z, cos Z are not bounded. Why? Because sin z and cos z are entire functions. Now, if they are bounded, then they will become constant functions by Liouville's theorem. But we know that sin z and cos z are not constant functions. They take several values. Okay? So, sin z and cos z are definitely not constant functions, but they are entire. So, they cannot be bounded. Okay? So, the proof is sin z, cos z are non-constant functions. Non-constant functions. Non-constant functions, and let me add one thing, that they are entire. Non-constant entire functions. So they cannot be bounded and thus are unbounded. Unlike in the real case, that is sin x and cos x, x is real, are bounded. They are between -1 and 1 in fact. But sin z and cos z are not bounded. We already saw this by directly writing real and imaginary parts of sin and cos. We write sin x cos y plus sin x sin y and so on, and then took the absolute value and saw that as y goes to infinity, mod of sin z goes to infinity. That also proves that sin z is not bounded. But as an application of the Liouville's theorem also, you can see that these functions are not bounded. Another application of Cauchy integral formula, or now you can say that application of the fundamental application of the Liouville's theorem. Let us prove fundamental theorem of algebra. Fundamental theorem of algebra. Now, as much one can say about the theorem, it is still less, because this is one of the pillars of entire mathematics, and then so many situations we need to apply the fundamental theorem, and the theorem stands as one of the most not only important but beautiful theorems in mathematics, and it was first proved by Gauss, the prince of mathematicians, and he gave a correct proof of the fundamental theorem of algebra for the first time. That was his PhD dissertation. All right. So a lot of history associated to this, and different proofs of this can be given. You have been using this in fact right from your first year BSc, but perhaps without proof. So can you tell me the statement? Is there anyone who knows the statement of the theorem? The theorem says that every polynomial has a root in C. Okay? Every polynomial with complex coefficients of course a non-constant polynomial with complex coefficients has a root in C. You have to take degree bigger equal 1. Of course, this is not true if you replace this C by R. There exactly we started, alright, that is x square plus 1 has no roots in C, therefore we get I. Okay. So this is polynomial which has no root in C, has no root in R, has no root in R, has no root in R. Okay. So, but then is there a polynomial which does not have a root in C? No, that will not happen. That is fundamental theorem of algebra. Give me any polynomial and there will be at least one complex number at which it is 0. Okay. And then once it has one root, okay, by factor theorem you can take out the factor and then you get a polynomial of lesser degree. But every polynomial has root, so that polynomial will also have root. So you will get again linear factors will come out. Okay. So this in turn means that every polynomial can be factorized into product of polynomials of degree at most 1. It is linear factors. Okay. So this theorem means every non-constant polynomial, I have to write non-constant anyways, I mean, because constant polynomial there is no question of root unless it is 0. So every non-constant polynomial can be factorized as a product of linear factors in C, linear factors over C. Over C means with complex coefficients. So for example, x square plus 1 you can factor as x plus I into x minus I. So the coefficients are now allowed to be complex. Then you can always get linear factors. You will always get linear factors. Any polynomial of any arbitrary degree you can factorized as product of linear factors, that is fundamental theorem. Or equivalently, you prove that given any non-constant polynomial, there is at least one complex number at which it is 0. Okay, that means it has a root. Okay, so this is a very celebrated result, and if you want to tell what you learned in this course, you can definitely say that we learned fundamental theorem of algebra, and then that would be impressive, I suppose. Okay, that means you have learned something which is substantial, okay, for the first course in complex analysis. Right. All right. So let us see the proof. So proof. Okay. So consider the polynomial. So let Pz be equal to A0 plus A1z A2z square An z power n, of course n bigger equal 1, n bigger equal 1, and we want to show that there is z0 such that Pz0 is 0. So to prove that there exists z0 in C such that Pz0 is equal to 0. That amounts to proving that this polynomial has root z0. and this is any polynomial. So every polynomial there will be some number at which it is 0. So now we want to show that such z naught exists. So suppose not. That means what? It is not equal to 0 at any point. Okay, suppose not. That is, Pz is not 0 for all z. Is this clear? We want to find one point where it is 0. Suppose not, then what will happen? That it is not 0 at any point. And then now we will have to arrive at a contradiction in order to prove the theorem. Okay. All right. So now this is not 0 at any complex number. Then you consider the function fz equal to 1 upon pz. What can you say about fz now? Since this is a polynomial, this is a rational function, and then denominator is never 0 by our assumption now. So denominator is never 0 means this function is analytic everywhere. So it is entire function. Okay. So since pz is not equal to 0, okay, for any z, all right. So since Pz is not 0 for any z, Fz is entire function. Fz is an entire function. Is this clear? Now, if we want to apply Liouville's theorem, okay, then if we show that fz is bounded, then it will be bounded and entire, and then by Liouville's theorem it will be constant. But we know that it is polynomial of degree bigger equal 1, so it is not a constant function. So we will arrive at a contradiction then. So if we want to prove the theorem, we now want to arrive at a contradiction, and then f becomes entire, so let us prove that it is bounded, okay, then it will become constant and we get the desired contradiction, okay. So we now prove that f is bounded, we now prove that fz is bounded, okay. Now let w equal to, let w equal to a naught upon z to the power n plus a1 upon z to the power n minus 1 up to a n minus 1 upon z. So how do you relate w to pz? If you see, then if you divide by z to the power n throughout to pz upon z to the power n, okay, you will get this w plus an. So note that, so observe that pz upon z to the power n is w plus an. Is this clear? So pz equal to w plus an into z to the power n. Therefore, pz is equal to w plus an to z to the power n. Now, if you consider these terms in W, okay, if you consider these terms in W, then this is A naught upon z to the power n, A1 upon z to the power n minus 1. So, as mod z increases, so suppose mod z is very large, then this will become small in absolute value. So, mod of this will become small if mod z become r, if mod z become large. Okay. So, we choose a certain number. So, let us choose here mod an upon 2n. So, consider mod an upon 2n. Okay. Remember, n is fixed. P is a polynomial of degree n. So, n is fixed here. Okay. N is fixed. So, this is a fixed number and this is a real number because you have taken absolute value of this. Coefficient an can be complex, but then this is absolute value. This is a positive real number. So, this is a positive real number. And then we can choose a real number r so that, so choose r positive so that if mod z is bigger than r, then each of the term here is less than mod an upon 2n. Then let me write mod ai upon z to the power I minus 1 z to the power n minus I, because a naught upon z to the power n, a1 upon z to the power n minus 1, all the terms are less than or equal to for all I. See this again. See this again. I have written these terms only, mod a naught upon z to the power n. See, for I equal to 0, this is mod a naught upon z to the power n. Okay. Shall I write this slightly bigger? Mod ai upon z to the power n minus I. That is a naught upon z to the power n, a1 upon z to the power n minus 1. That is these terms. Precisely these terms, their absolute values. Now, why can I find out this r such that if mod z is bigger than r, mod of this is less than or equal to this? Why can I do that? I can do that because this is fixed, this side is fixed, this is in your control. So, 1 over mod z will reduce as you will increase r. So, you can always compare with this and choose r such that if mod z is bigger than r, this quantity will be less than this. And then you do this for all and you can find a common r such that this absolute value is less than mod an upon this. So, mod w will be less than or equal to, now these are n terms, so mod w will be less than or equal to mod an. Okay. So, maybe this is an upon 2n. So, that is some number chosen for just adjusting the bound, that is it, there is nothing much. You can choose any convenient constant here, alright. This is useful in the proof, alright. Therefore, mod w, which is this, mod w means you take absolute value on both sides. So, mod of this, it will be less than or equal to mod of this plus mod of this plus mod of this. But each mod we have made less than or equal to mod an upon 2n. So, mod w is less than or equal to n times mod an upon 2n, that is equal to mod an upon 2. So mod an plus w, mod an plus w is bigger equal mod of mod an minus mod w, mod of mod an minus mod w. Why? Because you can think of this as minus minus w. Okay. So mod of a minus b is bigger equal mod of mod a minus mod b. Several times we have used this inequality. Alright. So but mod an is bigger equal 2 times mod w. Okay. Or you may write mod w. So this is bigger equal, alright, since mod w is less equal this and this is minus sign, so this is bigger equal mod n minus mod an by 2. See this, mod w is less than or equal to this. So minus mod w is bigger equal minus mod an by 2. So this will be equal to mod an by 2 again. So mod an plus w is bigger equal. Now look at this expression for pz. So what is pz? Mod pz is mod w plus an. So now mod pz is equal to mod an plus w into mod z to the power n. Okay. That will be bigger than or equal to mod an plus w we have just now proved to be mod an by 2. So mod an by 2 and mod z is bigger than r. So r to the power n. So this is true if mod z is bigger than r. So now in fact you may write strictly bigger because mod z is strictly bigger than r. So if mod z is bigger than r, this is already bigger than mod an by 2 and this is bigger than r to the power n. And then therefore fz, which was 1 upon pz, its mod is less than 2 upon mod n into r to the power n. Where this mod z is bigger than r. So there is some circle with center at origin, radius r, outside which absolute value of mod is less than a constant. This is now constant. So for all z here, mod fz is less than this. So what about this then? Now this disk is a compact set. So on this, any continuous function will be bounded. So, and further, since f is analytic, we have assumed that pz has no 0, which makes f analytic, and therefore what do we get? Since f is analytic, it is continuous, and therefore mod fz is definitely less than or equal to m for all z such that mod fz is less than or equal to r. So inside this disk, definitely it is bounded. Whatever I have written, even if you don't read, it is fine. What I want to say is that mod fz is less than a constant outside this, and this is closed and bounded disk, so anyways it is bounded on this. So f is bounded on entire plane. That is what we wanted to prove, that f is bounded. See, it is written here still. Read this. We now prove that f is bounded. Okay. Which we have proved. Outside the disk, we have found a bound. Inside the disk, it will be always bounded. So f is bounded on the entire plane. So f is a bounded function. It is bounded function on C. So f becomes entire and bounded, and therefore f is constant. So by Liouville's theorem now, by Liouville's theorem, okay. So now by Liouville's theorem, f is constant. Now by Liouville's theorem. Which is a contradiction, because Pz is a polynomial of degree bigger equal 1 and 1 upon Pz is Fz. So Fz cannot be bounded, a contradiction. And why do we get this contradiction? Because we assume that Pz has no 0 in C. So there exists some Z0 in C such that because we assume that there is no such Z0, no such Z at which it is 0, then we get a contradiction. So at least at some point it must become 0. So a polynomial always has a 0 in C. That is fundamental theorem of algebra. Okay. So every non-constant polynomial will have 0 in C, and therefore it can be expressed as product of polynomials of degree at most 1. So the proof is complete, and we can write by fundamental theorem what can you say? That a polynomial Pz, a polynomial Pz can always be written as Pz can always be written as Pz equal to an times maybe an z raised to n is the, so z minus z1 z minus zn. So one can always express a polynomial as product of linear factors. Okay, you can always factorize a polynomial with complex coefficient as product of linear factors. So remember, this is application of the Cauchy integral formula, because Cauchy integral formula gives rise to the formulae for the nth derivative, and the formulae for the nth derivative in turn gives rise to the expression, okay, is an upper bound on the nth derivative we get, and then we get the Liouville's theorem, and which in turn gives the fundamental theorem of algebra. So this circle of ideas associated with the Cauchy theory we have seen, all right. And then the statement that follows in this is, in this link, all right, is the maximum modulus theorem. Okay, maximum modulus principle. Okay. So a version of this you can think of, which we will actually state and prove next time. But then if you consider a point z0 and a neighborhood of this point, okay, in which suppose f is analytic, okay, so this is a delta neighborhood of z0, and f is throughout analytic. F is analytic. Then suppose if it happens that, so maximum modulus theorem states actually that the maximum of the absolute value of f will be attained on the boundary. So suppose this is, so function is defined in the neighborhood of this disk suppose, then if mod fz is less than or equal to mod fz naught for all z in this delta neighborhood of z naught, and if f is analytic in that neighborhood, then we can conclude that f is constant function. So this implies that this actually implies that f is a constant function. Okay. So proof of this we will see next time, so that we will again get chance to revise the ideas associated with the Cauchy integral formula, and then we will move to the last part, that is Taylor and Lorentz series expansion. So this integral formulae that we have learned, that is the expressions of the functions in terms of integrals, will be used to find out the Taylor series expansion of the function around that point. Okay. So that will be last part of this theory. So after proving the maximum modulus principle, we will go to series expansions and obtain Taylor and Lorentz series expansions. Okay. So that is what we will do